Okay, so I suppose we have to wait for attendees, right? Should we start right now or shall we wait a couple of more minutes?
You can start now.
Okay, so to the attendees, welcome to this session on synergies between climate change, energy access, and energy poverty. The first speaker is Benedict Jansen, University of Bern, Switzerland. I will give you the floor to yourself. Please kindly introduce yourself and then start your presentation.
Yes, thanks for having me here today. I'm Benedict, and I'm currently a PhD student at the University of Bern in Switzerland. And I will quickly share my screen with you. And full screen mode. All right, do you see the presentation?
Yes, it's fine.
Yes, perfect. Okay. So today I'm talking about the determinants, persistence, and dynamics of energy poverty, which I did together with Katharina Drescher, who's currently at Statistics Austria. And yeah, as I introduced myself before, I'm currently at the University of Bern. So before we talk about the empirical exercise that we did, I would quickly clarify the term energy poverty. So it basically it means that someone experiences an inadequate level of domestic energy services, but there's currently no uniform definition. Sometimes the literature also refers to it as fuel poverty when we talk about this in the context of developed countries, but we go with the term energy poverty because the EU just introduced primary indicators to capture that energy poverty in the European Union, which are arrears on utility bills, low absolute energy expenditures, a high share of energy expenditures on income, and inability to keep the house adequately warm. So in general, one could say that it's related to energy inefficiency, high energy costs, and also to low household incomes in general. So there are three approaches to measure energy poverty. I only listed two. So the first one is the expenditure-based approach, where we measure energy poverty based on the actual energy expenditures a household has. In this case, we go with the EU indicator, which says that a household is energy poor if the share of its income spent on energy is more than twice the national median. The other indicator is the other approach is the consensual approach, which considers a household as energy poor if the household self-reports an inability to secure a certain level of domestic energy services. There's actually a third approach to measure energy poverty, which is the direct approach, but due to unavailability of data, it is not really, at the moment at least, it's not really useful, because we don't have data on how much energy households actually consume. So what's the motivation of this paper? In the face of a just and fair energy transition, we have to make sure that especially low household incomes don't have the total burden of the energy transition. There are actually quite a lot of negative welfare effects associated with energy poverty, such as a reduction of mental and physical health, respiratory diseases like asthma, and there's also evidence on the reduction of children's educational attainment if a household is energy poor. So therefore, there's a requirement of targeted policy measures to tackle the issue of energy poverty. There's quite a lot of literature on energy poverty. Most of it started in 1999 in the UK and Ireland, and that's why most of the literature is still focused on the UK and Ireland. But there's also a growing number of studies on the prevalence of energy poverty in other European countries and other developed countries like Japan, the US, and a lot of studies in the European Union as well. Most of these studies are more descriptive and don't focus that much on the determinants of energy poverty. There are studies like the one from Healy and Clinch in 2004, who identify long-term ill and lone parent families as the most energy vulnerable households. And in the case of Germany, there's only one other study that considers the determinants of energy poverty, which is a study from 2019. And they find that income, energy expenditure, and employment status are main determinants of experiencing energy poverty. But most of these studies are carried out in a static context, which means they employ cross-sectional data instead of panel data. I think there are only two other studies that consider a dynamic context, and one of those studies is the one from Fimister et al. From 2015. They look at the evolution, the movement in and out of energy poverty in Spain. And Chaton and Lacroix, they look at evolution of energy poverty in France, and they find that energy poverty is mostly transitory. So we're doing an empirical exploration of energy poverty in Germany, and we're using the German socioeconomic panel, which is, I think since 1984, it's a household panel survey, and it includes a whole bunch of information on socioeconomic, socio-demographic characteristics, as well as housing conditions, and a lot more information like preferences, etc. We only used 3 waves from 2016 to 2018 because only in 2016 a question on energy poverty was introduced. So we can only use these 3 years. In the end, we obtain a balanced panel of 9,032 households, which is then over the 3 years around about 27 observations in total. If we look at the descriptives, at the distribution of electricity, heating, and energy expenditures, so the mean is around about 108 euros per month. In the socioeconomic panel, households, they report electricity and heating costs separately. So, and some only report electricity costs, some only report heating costs, and we add them up to get total energy costs that a household has to bear in a given month. So this is the distribution. We see it has a really long tail. So there are also some households that have monthly expenditures more than 300 euros, but it's only a few, so it's very long tailed. So then we looked at the distribution over the income deciles, and we see that the lowest income decile, the households in that decile spend nearly 14% of their income on energy expenditures every given month, whereas the highest income decile households in there only spend 3.24% of their income on energy expenditures. But if we look at the energy use intensity, which is basically spending per square meters, we see that it decreases. So households that are in higher income deciles spend less money on energy per square meter than households that are in the lowest income deciles. And it kind of indicates there are some energy inefficiencies in the lower income deciles, which may be due to housing inefficiency, but maybe also due to inefficient use of energy sources. So our empirical strategy is twofold. We first employ a dynamic random effects Probit model, where we try to identify the driving factors of energy poverty and try to estimate the persistency of energy poverty in Germany. And we then employ an identification function and use a multinominal Logit model to work out differences between chronic and transient energy poor households. So our dynamic random effects Probit estimator is basically a normal random effects Probit model, where we include the lagged dependent variable. It's the YIT minus 1. Then we have a vector of explanatory variables or covariates like housing conditions, income, labor force status, and so on. And we include the heterogeneity, like the household specific term, to allow for heterogeneity across our households. But if we only estimate this model, we have a problem with the initial conditions, because we don't observe the process right from the beginning, because we just jump right in 2016. And the energy poverty status of the household in 2016 is probably will bias our estimates. So we have to specify a distribution of heterogeneity conditional on the energy poverty status of the household at the beginning of our panel. So we model our individual household term as we include the in-sample mean of our exogenous covariates and our initial energy poverty status of at period 1. And then we can estimate our full model, where we include our specification of the individual term. And then we can estimate our model and get more or less unbiased results. We then employ an identification function to distinguish between households that are chronic and transient energy poor. So this identification function basically identifies how many periods a household spends in energy poverty. If it spends 0 periods in energy poverty, we consider it labels the household as 0, as never energy poor. If it spends all periods in energy poverty, we label the household as always energy poor. And everything in between we label as transient energy poor. So it's basically households that are going in and out of energy poverty, or that only experience energy poverty once. And we then employ a multinominal Logit model, where we set never energy poor as our reference group to work out the differences between these 3 groups. So it's still a work in progress. So these are only our preliminary results. I think this is a bit small. Maybe I can zoom in. All right. So the first 2 models that we estimated were the models where the model 1 and 3 were the models where we did not include where we did not control for the initial condition. So we see that it gives us an estimate of 37.3 or 21%, which basically means that if a household was energy poor in the previous period, the chance that it's energy poor in the next period increases by 37.3%. So which is quite high. When we then included when we then controlled for the initial condition, we still got an estimate of 19.8%. So basically, if a household is energy poor in the previous period, the probability that it's still energy poor in the next period increases by 9.8%. But also we see that we have a significant estimate for the initial condition, so which is strong favor of controlling for the initial condition in that case. We then included some covariates like the household type, where we identified vulnerable groups like single parent and 1-person households, whereas households that are like couples or coupled with children, they are even less likely to be energy poor. We mainly included education and labor force status to control for income. So most of these effects in education and labor force status are probably income effects, but it might also be the case that having no degree decreases the probability of having like energy efficient use of your energy sources. So this might not always be income effects, but also behavioral effects sometimes, but in this case we can't separate them. We then included some household characteristics, like the build construction year of the building and the main heating type. And we saw that especially households that live in old buildings that are not well insulated, and households that use oil or electricity as their primary heating source are especially vulnerable to experience energy poverty in Germany. We then included a dummy on which indicated if a household has concerns about the climate change to get some behavioral effects maybe, but we saw that it's not significant in that case. So, but these are still preliminary results, as I said, so we still have to work on that. And then these are the results of our identification function. So we saw that we had 9,032 households in total, and out of these households, 7,300 households were never energy poor, 1,300 experienced energy poverty once in the observation period, so we labeled them as transient energy poor, and only 400 households experienced energy poverty in all 3 periods. We looked at the consensual indicator. We had even less households that reported inability to heat their homes during winter. So we were only 0.4% of all households in our panel that said in all 3 periods that they have problems heating their house during winter times. And 8,649 households were never energy poor at all. So what is the conclusion of this? Well, it's basically important to understand the determinants and the dynamics of energy policy, it's crucial for policymaking. We saw that the expenditure-based energy poverty is higher than the consensual energy poverty. And we also found some evidence that there is some persistence in energy poverty, especially in expenditure-based poverty. But all in all, it's more of a transitory state in Germany at least, and than a chronic state. So there are some problems and caveats with our study. We still have to figure that out. We're still waiting for another wave of the German Socio-Economic Panel for the year 2019, because actually we only have 3 years. That might be a bit less and we don't observe efficient movement in and out of energy poverty. So we hope to get another wave, like in December or in January. We have to wait to include the population weights. We didn't do that yet. We can't consider the depth of energy poverty with our identification function because we only know if a household is energy poor or not. So we don't know how far away from the poverty line the household is. We're still looking for a solution for that. All right, thanks.
Thank you. Sorry for being so present, but it's my role. Yes. Okay, so I see that there are no external attendees, so we are all here, all the speakers and participants. So if there is any question, we can ask directly to the speaker. If there is no question, I would start with a question. Okay, so you mentioned at the beginning that you consider a balanced panel. I wonder how this can affect your result, in particular the result of the original status of being poor or not, because I suppose that the panel is balanced because it does not include families that come into the survey or opt out of the survey, but I wonder how independent is the probability of joining the survey and leaving the survey from being energy poor or not. For instance, I don't know the characteristics of this survey, but if the survey includes, for instance, if new families of immigrants, for instance, they're probably more likely to be in energy poor than the one in the energy poor status than the one already present that were already present in the panel. So this can probably bias your results. Have you thought about it, and have you thought how to try and solve this?
Yes, thanks. That's a great question, and we we actually thought about it. Luckily, the German socioeconomic panel, they quite well document what households drop out of their survey and why they drop out. And it aims at being a representative survey of the whole population. So that shouldn't bias the result in itself, but like the dropout out of the panel, that might be a problem. But that's why we still have to include the population weights. So if we include the longitudinal weights, that should more or less help to reduce the bias of the estimates.
Okay, thank you. I ask if there's any other question. If not, we move to the second speaker. Thanks for your answer. Is there any other question? No, so please stop the sharing. Yes. Thanks. And the floor is to Isabella Aloisio, right?
Yes, correct.
Please share your screen and you can start.
Can you see it?
Yes.
Screen? Yeah, great. Okay, so my name is Isabella Aloisio and I'm a research associate at Florence School of Regulation, Energy and Climate at the European University Institute in Florence. So today I will present you a paper on the synergies and trade-off between energy access, climate change, and water use in Sub-Saharan Africa. Okay, so the water, energy, food, and climate nexus is at the center of Agenda 2030 for Sustainable Development. It tackles simultaneously food and water security, and the connection between global warming and water scarcity, and between climate change and energy security, as well as the connection between energy production and water and the land use. The paper, which is still in a, let's say, in a first phase, so it needs to be developed further, but aims to analyze the synergies and trade-offs between energy access, climate change, and water use in Sub-Saharan Africa. The nexus can be divided in different sub-themes, and the paper will only tackle on the highlighted interactions, namely water-energy nexus, climate change energy nexus, with a focus on climate change and renewable energy, and climate change and energy access. So let's say SDG Sustainable Development Goal 7.1 and 7.2. And with the further analysis on the relation between energy access and greenhouse gas emissions. And finally on the relation between climate change and water nexus. So the paper novel approach is meant to be represented by the analysis of the water, energy, and climate nexus under the energy access perspective, including so not only the impact of growing energy demand on CO2 emissions, but also the impact of climate change on energy supply and water availability, as well as linkage between climate policies, energy prices, and therefore affordability of energy access in Sub-Saharan Africa. So current climate change projections show that crucial changes in the temporal and spatial distribution of water resources and the frequency and intensity of water-related disasters rise significantly with the increasing greenhouse gas emissions. So climate change will have an impact on water availability and therefore and subsequently on energy supply and demand. There are global projections that are very clear, underlining that not only the pressure of climate change, but also population growth and economic development and urbanization really put a pressure on the demand for fresh water and energy. And global water demand is projected to increase by 55% by 2050. And then global energy consumption is projected to grow by 1/3 by 2050. And we know that of the, let's say, number of people without access to electricity worldwide, 90% live in Sub-Saharan Africa. And this number is not going to improve. Indeed, as we see in this figure by the World Energy Outlook, it's a special report on energy access. We see that whereas China and India, well, China already achieved electricity access in 2015. India will achieve it by 2025, but Sub-Saharan Africa by 2030 will only gain a small percentage of access, and the 9 out of 10 people without access will be in Sub-Saharan Africa by 2030. And today only 43% of population have access to electricity in Sub-Saharan Africa. So, and in this other figure, you can see that half of this comes from the IEA New Policies Scenarios up to 2030. Half of those people gaining access by 2030 will do it via grid, so via centralized grid. But in Sub-Saharan Africa, off-grid and mini-grid systems will generate the majority of the electricity access. And another relevant information from this figure is that more than 60% of those gaining electricity access by 2030 will do it through renewable energy sources, and more specifically solar and hydro. So this the bulk of rest of renewable energy sources in electricity access will be solar, mainly by solar and hydro. So first we start with the water-energy nexus. So water and energy are closely interlinked. So energy is required for the extraction, treatment, and distribution of water, and water is needed to produce and transport almost nearly all forms of energy. But unlike energy, the energy sector can switch to other resources, and this we'll see, for instance, solar and wind energy. So intermittent renewable energy resources, such as wind and in this case photovoltaic solar energy, have a negligible use of water. On the contrary, hydropower, concentrated solar power, and biofuels have a very high water footprint. And among the non-intermittent renewable energy sources, the geothermal energy power have low water footprint. Then if we analyze the fossil fuel energy sources, thermal power plants use large quantities of water for cooling. And if we add up CCS systems to the plant, then this will have even higher water footprint. In the case of shale oil and gas extraction and production, this is more water intensive than conventional oil and gas. And when we associate carbon capture and sequestration to bioenergy, this has important drawbacks in terms of higher water as well as land use. So climate change has an impact on both energy demand and supply. So now we analyze the relation between climate change and energy. So climate change has an impact on both energy demand and supply, and on the reliability of the whole energy system. And on the demand side, the rising temperature changes the balance of heating and cooling demand patterns, whereas on the supply side, the impact include changes to the average and variability of solar, wind, and hydropower resources. But the paper focuses on the climate impacts on the supply side and tries to suggest the most resilient energy production systems for Sub-Saharan Africa. So hydropower is vulnerable to climate change, and impacts are globally unevenly distributed, and they are mainly local impacts. So in the southern hemisphere, decreasing rainfall is expected to cause a reduced hydropower production, as is the case of Southern and West Africa. And whereas on the opposite side, Eastern Africa will experience risk of flooding. So a high percentage of rain precipitation with the risk of flooding, leading to likely damage of hydropower dams, such as the case of Kenya. Climate change has a relevant impact on intermittent wind and solar energy. And the geothermal energy is less dependent on climate conditions. So the projections are, let's say, projection of climate change impacts on water resources in Sub-Saharan Africa, and not only, I would say globally, come with large uncertainties. So, but the most important data that we have for Sub-Saharan Africa is that the countries which depend on hydropower for 90% or more of their electricity generation will be highly impacted by climate change. So then I will go through to analyzing two different trade-offs. The first is climate change and energy access. The second will be climate change and energy prices. So if we talk about climate change and energy access, with the premise that decoupling greenhouse gas emissions and growth is absolutely relevant for developing countries, we analyzed energy access and greenhouse gas emission and greenhouse gas, mitigation, greenhouse gas emissions. And according to the literature, there are quite contradictory picture, but that, I mean, they stand for basically three main literature. One is the International Energy Agency, which estimates that achieving Acces by 2030 would increase electricity consumption by 2.5%. And fossil fuels by 0.8%. According to Chakravarti and Tavoni, they assessed that the global final energy consumption increase of about 7% by 2030, with achieving a full energy access, and the bulk of this will be in Africa, where final energy consumption need to double with reference to a scenario without energy poverty policy. According to Pachauri et al., achieving a total rural electrification by 2030 will increase emissions by about 2.2 and 4%. So this said, the most interesting figure in our study is that according to the relevant literature, the share of Sub-Saharan Africa in global electricity related emissions is projected to be very small. So compared to global emissions, and this is only 0.7% by 2030. And this is due mainly to two drivers. One is the fuel switch, so from fossil fuels to renewable energy, basically from coal, mainly from coal to renewable energy. And the other one is use of more efficient coal and gas power plants. So one is fuel switch, the other one is energy efficiency. And however, this figure is offset by a growing use of coal in Southern Africa. Access to electricity has other co-benefits. So, for instance, switching from kerosene to electric lighting, reducing black carbon emissions. So basically health benefits. And so in Sub-Saharan Africa, climate mitigation policies could offset the projected greenhouse gas increase, thanks to efficiency improvements and a shift to RES. The other trade-off that I analyzed in the paper is between climate change and energy prices. So we know that climate mitigation policies can negatively impact energy access by increasing energy prices. And this has a very high impact on energy pools in developing countries. So in Sub-Saharan Africa, the highest increase in energy prices happens in those regions with largest share of fossil fuels in their electricity mix, which is quite a good news, I would say, because if we analyze the data here, energy price increased by 40% in Southern Africa by 2030, due to the dependency on natural gas, for instance, in Angola, Mozambique, and Tanzania, whereas South Africa is dependent mainly on coal. The price increase is 35% in Western and Central Africa, where these countries in these regions depend mainly on natural gas and hydro power. Whereas in Eastern Africa is the region that has the lowest price increase by 2030, namely 25%, due to the largest share of renewable energy in the electricity mix, geothermal, hydro, and wind energy. So to present the results and conclusions, so providing universal access in Sub-Saharan Africa is expected to have a negligible impact on global CO2 emissions. And the climate mitigation policies could offset this small increase by a shift to renewable energies, especially solar PV, wind, and geothermal, allowing for a more sustainable and resilient energy supply and a more affordable energy access and a more efficient water use. So it's a real win-win solution. And then a coherent carbon pricing policies and consistent low carbon energy investments would also allow Sub-Saharan Africa countries to meet their climate targets and to cope with climate change impacts and fill their energy access gap. Here I will present some briefly some concrete solutions that are just some of the ones that I presented in the paper, concrete solutions to the WEF Climate Nexus challenges in Sub-Saharan Africa, but they can be applied in all countries, especially developing world. So enhancing of grid systems, especially mini grids based on hydro, solar, and wind, the so-called last mile challenge. Then shifting from fossil fuels to renewable energy using, for instance, photovoltaic energy for water desalination, or also to produce hydrogen, using seawater electrolysis would reduce freshwater use, more energy efficient. Then reducing on the water side, reducing freshwater demand in energy production by using marginal water, or developing multi-use reservoir to increase the total water use efficiency of hydropower compared to traditional dams. And climate change challenge. So to conclude, climate change challenge is a challenge, but is also an opportunity for overcoming technological lock-ins and promoting the use of renewable energy sources in Sub-Saharan Africa. So thank you. I finish with the presentation.
Thank you very much. Excellent timekeeping. Very few seconds over. Again, we are the five of us. So I would ask if there's any question from the other speakers. If not, I will ask a question myself about the water electricity nexus,
Yes.
in particular the causality of the relationship. Now, as you said, there can be a double causality, because we need water to produce electricity for some technologies, not all, but several, and electricity can be used to produce water, desalinization, for instance, or even to transmit it, transport it, etc. Now, to the best of my knowledge, but please correct me if I am wrong, in developed countries, in OECD countries, for instance, except for some exceptions, like it comes to my mind the case of Singapore. So except for some exception, the biggest causality goes from water to electricity, because the water need on electricity production is much higher than the electricity needed for water production. How about low developed countries, in particular African countries? Which one of the two causal relationship dominates? And what about the perspective dominance in the future, also taking into account the climate change issues?
Sure. Yes, you're right. I mean, water for electricity is very relevant, and in Africa we know that not only due to climate change, but due to the water resources that they have, even at current level, is a problem, is an issue. So this is why the renewable energy could really play a role Of course, not all renewable energy, and I mean sometimes hydropower is not even considered renewable energy, so it depends. But let's let's consider it among the renewable energy. But this is, of course, is very energy intensive. Sorry, water intensive. But there are other sources, for instance, wind energy and solar PV, because this is different from concentrated solar power, where you need a lot of water to cool down the plant, as in other thermal power plants. But wind power and so onshore, offshore, whatever, and solar PV, as well as geothermal, are the three sources, the three, let's say, best sources in terms of less water consumption. So, I mean, this is my study. Of course, we know that the bulk of renewable energy sources in Africa, in Sub-Saharan Africa, is hydropower and solar, and mainly hydropower, I would say. But as we saw during the presentation, this is really has very high impacts from climate change. So not only hydropower needs, needs, of course, I mean, uses water to produce electricity, but this water is really not the right quantity of water, because there's a problem when you have too much water. Like in Eastern Africa and Kenya, as we saw, or you have too less water in the case of Southern Africa, especially South Africa and other countries in Southern Africa and West Africa, like in Ghana, for instance. Ghana had to rethink completely the electricity supply side because of problems with hydropower sources, because of lack of rainfall or too small rainfall. So yeah, so wind and solar PV and the geothermal energy, where is present, of course, it's according to my studies, the best for Sub-Saharan Africa.
Okay, thank you. We'll quickly ask to move to the next speaker, because we are running a bit short of time. Thanks for your answer. Next speaker is Alessandro Fiorini, right?
Yes.
Please start.
I share my screen. Okay. Can you see it?
Yes, go ahead.
Okay. Hold on a second. I try to manage the setting. Okay. Thank you very much for giving me the opportunity to deliver this presentation, and thank you everybody for attending. I am Alessandro Fiorini. I am a researcher in the Energy Efficiency Unit of the ENEA, which is the Italian National Agency for New Technologies, Energy and Sustainable Economic Development. In particular, I am a member of the Policy Monitoring Lab. This is the outline of my presentation. I start with some comments around the background of the study and the research question. Then in the second part, I dig into the empirical approach used to address and answer the research question. And then lastly, I discuss achievements and future improvements of this study. So let's start with the first part. So the third energy package of the EU issued in 2009 called member states to develop a definition of vulnerability of consumers with respect to energy needs. Then to bridge this problem to the occurrence of energy poverty and to give an assessment of the size of these problems in each country. So after 10 years, what is the state of the art with respect to definition and measure of energy vulnerability and energy poverty? Well, there is a growing literature on the topics, as Benedict showed also in the beginning, but there is a tendency to deal with energy poverty and energy vulnerability as two separated issues. And energy poverty is gaining more attention, way more attention with respect to the concept of energy vulnerability. And despite this effort, is not emerging a prevailing approach. Analyses are weakly replicable or not easily replicable, let's say, because they are very specific to the context, to the case under exam, and in general, energy poverty analysis do not move sufficiently away from the triadic specification of the occurrence of three causes like low income, high energy prices, and low energy performance of the buildings. Policymaking also reflects this lack of uniformity because either energy poverty is not recognized as a problem per se, untied from poverty in general, or if specific targets are set out, they are based on some of the countless definitions and indicators available, sometimes also contradictory about energy poverty. So what suggestions from this study? So first of all, energy vulnerability and energy poverty must be tackled as two faces of the same problem. How? Reinforcing the interpretation of energy vulnerability as an ex-ante status, in which an ex-ante status characterized by factors of risk to fall into an ex-post condition of energy poverty. And this is what is done essentially in this study, where we center the focus on energy vulnerability and try to give a more formal characterization of the topic, taking into account both micro and macro, direct and indirect determinants of people's energy use, which is the actual source of the multidimensionality of the problem and the actual source of the vulnerability faced with respect to energy needs. And then build a measure which is coherent, a measure of energy vulnerability, which is coherent with the observed dimension of energy poverty. The methodology is consists of 3 steps. In the first step, we select a set of variables which define vulnerability with respect to energy needs at households level, and we turn the range of values or categories of these variables into a risk-like measures, inverted commas. In the second step, we use an econometric model just to test the relationship between this risk measure and an indicator of energy poverty. And in the third step, we built an energy vulnerability indicator at regional level, Italian regions, that takes into account a micro component, so the households level of analysis, and a macro component, so the contextual level of analysis, namely the contextual, I mean the regional environment. So for households level variables, the risk measure is obtained by assigning to each range of value or category a weight which is proportional to the estimated parameter in a simple logic model between the variable and the indicator, the energy poverty indicator, setting the highest level of exposure equal to 1 and the lowest equal to 0. In case of macro variables, so contextual variables, the risk measure is obtained running a range standardization of the values. The energy poverty index used is the one developed and adopted by the Italian National Energy and Climate Plan, which was developed by some scientists of the Bank of Italy, and takes into account these two couples of condition based essentially on the level of energy expenditure and the income. So the households level variables are grouped into 7 dimensions. This is the first one regarding personal characteristics of the household's head and the components. So we have the age of the household's head. H stands for household head, while a double H is for household's components. So then the number of components, the number of underaged children, the maximum level of education in the households, the tenure type, and 2 dummies for gender and nationality of the household's head. Dimension number 2 is about housing condition. So we selected the year of construction of the building and the square meters available for each component in the apartments. Dimension number 3 is about the economic condition. So we put the work condition of the head, the sources of income in the households, the current condition explained by these 4 categories, and the income use. Dimension from 4 to 6 are more directly related to the use of energy within the households. So we have the availability of basic home appliances, the availability of ICT devices and the connection to the networks, and the availability of electricity and gas carriers. And dimension number 7 is a focus on space and water heating systems and the availability of heating, cooling, and ventilation. Well, this is an example of the construction of the risk-like measures, as I said in the beginning. In general, we had not many surprises with respect to the expected sign and ranking of the values in terms of their risk. For example, you can see that for current condition, economic condition of the households, insufficient is the category with the highest, that gives the highest levels of exposure to energy poverty, while good is the lowest. In some cases, a reflection is needed because, for example, regarding the working condition of the households, we got retired as the best category, or, for example, the sources of income, it's rent from real estate properties. This is the output of the econometric model. It's a Logit model. I want to stress the point that this is not aimed to check the causal link between these variables and the energy poverty index, but it's just to check let's say the sign of the relationship and the degree of association between the variables. This is the best one we got. It's still a preliminary exercise, but this is the best one because actually we aggregated some variables like electricity and gas dummies together. We excluded some other variables, like, for example, the heating system type was not, the categories were not significant at all. And there was also collinearity with the water's heating system variables. And we got in case of gender of the households head, we got a better estimate combining it with the number of underaged children, and this can be probably have let's say, an interesting interpretation. Another interesting result of the model is the presence of non-negligible effects at regional level. So this was an hint to further indication to provide an additional analysis of vulnerability at contextual level. Taking the average of the values obtained for each variable and each households, we got this regional indicator from the micro perspective, and we broke it down for each dimension of the variables. So the different shades from red to green give an appraisal of the ranking of the regions with respect to these measures. You can see that, for example, in some cases, there is a clear clustering between north and south, in which we can identify an advantage for the northern regions, like for basic appliances, economy, and the housing condition. In other cases, maybe, again, we need to go in depth with the analysis. The macro indicators are built under 5 dimensions. For climate, we choose both heating degree days and cooling degree days. In parentheses, we put the expected sign of the direction between the variable and the energy poverty indicator. We represented market openness using data about market share of the top 3 electricity and gas providers and the switching rates, the domestic switching rates. Then we took into account the global wealth and energy consumption, respectively, with the GDP per capita and the final residential consumption per capita. And then also an indicator of the technological lead at regional level with the granted patents in the energy efficiency actions of the set plan, action number 3 and number 5. These are the results for the macro-based indicator. Again, you can have an idea about the positioning of the regions in terms of their vulnerability, looking at the different colors. It's interesting to notice, for example, that, for example, in climate, there is a better positioning for the regions in the center, of course, because either in the north they are in a condition in which there are severe winters, or in the south the opposite. I mean, severe summers. Technological lead. One, okay, yeah. Technological lead, there is a clear advantage for the north. So here I put together the micro and macro based indicators. The micro is more smooth across all the regions, while the macro gives a more there is a more heterogeneity, let's say, among the regions, maybe because the micro is based on averages over a huge number of variables. But in general, they give a coherent measure of energy vulnerability among them. I mean, they reflect a proper ranking of the regions with respect to the risk of falling into energy poverty. And they are also consistent with the measure of energy poverty that we have selected. You can see in these tables on the left-hand side that there is the results of 2 independence tests, one parametric and the other one non-parametric. And there is a huge association between these indexes and the energy poverty indicator. And it's interesting to notice that if we put them together, the correlation, let's say the association, increases. On the right hand side, I put the general indicator, which is the aim of this idea. I mean, it's the to build actually an energy vulnerability indicator. I put ideally some different categories, like in red for a high level of risk, in yellow moderate level, and in green low level.
Sorry, you need to.
So yeah, okay. Yeah, I was just discussing the achievements. Just well, regarding the future developments, it's of course we need to do a thorough understanding of the drivers, and maybe to find a better way to run the computation of the indicators.
Okay, thank you. Sorry for having interrupted.
No. I understand.
Okay, is there any question? Okay, I have more a kind of a comment than a question. We have 2-3 minutes at most, so let's try to be 2 minutes at most. I'm not too sure how coherent is the analysis you have developed with the interpretation of the single measure in terms of energy vulnerability. I mean, if energy vulnerability is something that occurs ex ante and energy poverty ex post, then there is a causal relationship. You mentioned clearly that you do not study causal relationship. So what you effectively have shown us is it's a linear combination of factors that can be translated into a single scoring measure. Basically, this is what the econometric model shows. You conjecture that some elements can be relevant for energy poverty, and you test which ones are significant from a statistical point of view. You get the parameters, and then given that the model rescale into a 0-1 score, that's basically a linear combination of significant factors into a single measure. So if this is, given what you have provided us, basically your value, your single score, it's just a synthetic way to represent a complex phenomenon, the energy poverty. It's not really a measure of something that occurs, and because of that you fall into energy poverty. So apart from the fact that it's a scaling into 0-1, there is nothing that really characterizes that as a probability of being energy poor, and therefore that can be defined as energy vulnerable.
Yeah, I see the point. Well, this is it's not really a preliminary result. This is a preliminary idea. The point is to focus on elements of vulnerability. I mean, the idea is that if we check the differences among groups of people that are identified in energy poverty, we are not approaching the problem from the right hand side, from the right side, because there is an indicator, there is a definition, and we identify a group of people, a subpopulation that is defined in energy poverty, and then we see if there are differences in terms of well, income or working condition or whatever. So the point is to move from what we call the ex ante point of view. Of course, the end of the story is to check if is there any causal relation between this measure we are proposing and the energy poverty measure. So it's a very preliminary reasoning. So about the multidimensionality, yes. Again, we at this stage there is nothing that can be interpreted as a probability, but well, there is the idea to try to formulate a risk measure that can be interpreted as something that then can be well,
okay,
can give a measure of the exposure to an energy poverty condition.
Thank you. Now we'll move to Paola Casati, right?
Yes, thank you.
Please share your
quickly
screen.
share the screen. Okay, can you see it?
Yes, please go ahead.
Perfect. Thank you very much. My name is Paola Casati, and I'm a junior researcher of the Sustainability Lab at SDA Bocconi. And in particular, I am part of the Just Energy Transition team. So today, I would like to introduce you the case of cobalt, a very complex case that deserves a lot of attention due to the severe criticalities affecting its extraction in the Democratic Republic of Congo. And in particular, I would like to tell you why cobalt matters so much and why the case of cobalt mining in Congo is so dramatic, focusing on the so-called artisanal mining sector. Then we will go deeper, analyzing the sustainability concerns affecting cobalt mining in Congo, trying at the end to enhance the role of artisanal mining for a more inclusive and sustainable supply chain. The current transition to a more sustainable energy system involves the worldwide use of clean technologies that often require the employment of certain natural resources, some of which are particularly abundant on the African continent. One of the most relevant examples is represented by cobalt, an element that has become essential for the transition, for energy transition, to the point that it is often called blue gold. Cobalt is a fundamental component of lithium-ion batteries, which are increasingly used for energy storage systems and electric vehicles, due to its particular chemical features, able to provide simultaneously thermal stability and high energy density, allowing batteries to function safely and for an extended period of time. But cobalt is also relevant for other applications. It is used for the production of alloys in the aerospace industry, for instance. It is used in healthcare, in catalysts, inks and pigments, and electronics in general, so your mobile phone and your laptop. So for many of us, it's an unknown component, but actually it's heavily affecting our everyday life. So cobalt demand is considerably growing during the last years, and by the end of the current year, it should exceed 120,000 tons. From the blue section of the pie chart, you can see that cobalt is becoming increasingly important, considerably important for the lithium-ion battery industry. And according to forecasts, by the end of this year, 75% of lithium-ion batteries in the world will contain cobalt. This is a stunning number, and even more impressive is that the electric car market alone would capture 1/5 of the total cobalt demand. As we have witnessed before, the Democratic Republic of Congo plays a crucial role in cobalt production. In fact, 71% of the world's cobalt is extracted in Congo, right in the middle of the copper belt, a region known for the wealth of copper and cobalt. And here it's important to mention that generally cobalt is a byproduct of copper. Congo is among the world's richest countries in terms of natural resources, but its people remain among the world's poorest. And Congolese mining sector has attracted billions of dollars in private investment over years, but these deals have generated limited public benefits due to corruption and bad governance. Here you can see just a graph showing you the magnitude of the production in Congo with respect to other parts of the world. And at the international level, China has a dominant role along cobalt supply chain. And as you can see from the bar chart, the supremacy of cobalt production is shared between several Chinese-owned companies and the Swiss company Glencore. Furthermore, as shown in the pie chart, China is the world's leading producer of refined cobalt, most of which produced from partially refined cobalt coming from Congo. I would also like to say a few words on cobalt prices, actually equal to $32,000 per ton. That would allow me to introduce you the core of our research. Cobalt is an extremely volatile metal, as you can see, and this is bad news for businesses. And as you can see, cobalt price collapsed starting from 2018, putting a strain on the economy of Congo. And this trend is mainly due to the fact that the market has been overwhelmed by a surge in supply of the metal from Congo, especially coming from artisanal individual miners. So artisanal mining, also called small-scale mining, it's a mining activity not run by the biggest players, but by small groups of people. And as you can see on the right side, the majority of worldwide cobalt supply comes from industrial operations or large-scale mining. However, 90% of cobalt miners and their families rely on artisanal mining as a primary source of income. And this is a very impressive number. Their output, as you can see from the pie chart, has considerably increased over the past years due to the growing demand for cobalt, especially for lithium-ion batteries. But it's actually much smaller with respect to that of industrial mines. And this is due, as we said before, by the fact that this sector is highly inefficient and highly unregulated. In particular, it is estimated that at least 100,000 people dig every day underground tunnels with their hands or very rudimentary tools without any protection, supervision, or social security. And according to estimates, children in the artisanal sector make up about 13% of the workforce, almost half of whom are under 14 years old. And accidents are often fatal, are frequent, considering the precarious conditions in which these miners work. Artisanal miners are independent workers working on illegal areas and who sell cobalt to intermediary traders in local markets, who in turn sell it to the large companies that dominate the Congolese mining sector. And the price miners receive directly from for selling cobalt purity to intermediaries in the supply chain is less than half, and potentially as low as 6% of the price by weight for the equivalent cobalt purity that traders obtain from their sale. So if traders receive $50 per kilogram, informal miners receive only $3 per kilogram. And looking again in more detail at the graph showing the distribution of miners between the industrial and the artisanal sector, we can see that 74% of the workforce is dedicated to pure artisanal mining. However, 16% of informal miners work on abusive industrial concessions, and this reveals the strong interconnections between artisanal and industrial mining. So we have basically two major issues affecting cobalt mining in Congo. The first one is the security of supply, that is a global concern related to the concentration of cobalt production and refining within two single countries, Congo and China. And this implies that a huge chunk of the cobalt supply chain is vulnerable to disruptions. And the second issue that is the focus of this research is related to sustainability concerns affecting cobalt mining that are exacerbated in the artisanal mining sector since it's completely unregulated, as we have seen. And here you have a detail of the most severe sustainability allegations received by the largest companies extracting cobalt, especially concerning child labor, hazardous working conditions, health issues, and severe impact on local population living near mining areas. Then we have the environmental impact. in particular air pollution, environmental degradation and contamination. And finally, serious socioeconomic problems that arise mainly related to corruption. Poor governance and corruption has allowed the country's largest state-owned mining company, Gécamines, to engage in opaque mining deals that failed to serve the public interest. And consider that according to Global Witness, more than $750 million of mining revenues paid by companies to state bodies in Congo was lost to the treasury between 2013 and 15. This sadly means that wealth escapes from the country and cannot benefit communities. Actually, there are three kinds of developments in response to sustainability issues affecting cobalt supply chain. One is actually the shift to other alternatives. So a lot of companies are trying to make a zero cobalt battery, such as Tesla, and it could be the way forward, but not necessarily a solution for Congo, as we will see shortly. There are some initiatives also from the Congolese government that, after having increased the royalties to 10%, recently created a state-owned company to buy all cobalt mined in the country. So this company is a subsidiary of Gécamines that, as we have seen before, suffers from serious corruption problems. And we don't know if artisanal miners could really benefit from this. So something is happening, something is changing in terms also of the traceability of the supply chain, but so much needs to be done. And obviously, there's big pressure on companies to address sustainability concerns, and an increasingly number of companies such as Tesla, Volvo, and Apple are implementing rigorous systems for monitoring and addressing sustainability issues throughout their supply chains, trying to stop the procurement of cobalt from artisanal miners. However, and this is the core of the research, by shifting demand away from artisanal and toward industrial mining, end user companies may further feed the corruption in Congo. And this is also due to the fact that these sectors are intricately intertwined, and companies would inadvertently continue to source from artisanal miners. So one thing that should be clear, and this is the most important point I want to stress, is that the solution is not necessarily to simply get rid of artisanal mining. You could make it forbidden, but a new black market would be created and hundreds of jobs would be lost, with detrimental effects on a huge number of Congolese families relying on small-scale mining. And don't forget the overlap that will continue to occur between artisanal and industrial mining activities. So disengaging from this sector would not represent a solution, because you would actually make the situation worse for the local population. And not everybody can work for the larger organizations, and artisanal mining represents one of the most important sources of livelihood for Congolese family, and could play a more prominent role in the country's economy if practiced in a regulated and supervised manner. A successful and replicable example is that of the Energy Resource Governance Initiative, founded by the governments of Canada, Botswana, Peru, Australia, and the US, in order to promote a solid governance and efficient management of energy supply chain in the mining sector. So concluding, we have seen that cobalt is an essential element for energy transition, but it is strongly linked to controversial mining practices that in the future could lead its largest consumers to seek for a substitute for it. And companies are trying to take some steps with the clear aim of protecting themselves and promoting more ethical and transparent practices. But on the other hand, if the objective remains only to free themselves from the informal sector and clean up supply chains, such actions may prove inadequate in facing the issues related to cobalt mining, leading to their further radicalization. And instead, the commitment to promote and regulate artisanal mining, to create a diversified and inclusive mining sector, could strengthen these vulnerable and unstable foundations upon which I believe that is developing not only the transition to renewable energies, but the entire future of our planet. Thank you very much for your attention.
Thank you, and I should also praise you for the excellent timekeeping. Okay, so we have 10 minutes left before this session is automatically closed. We've been able to save some time, so I would thank all the speakers. I would ask again if is there anyone who wants to address a question to Paola Casati, to her presentation. Yes, please. Is there a question?
Yes, I have a question.
Please go ahead.
Yes, I was wondering, you mentioned that Tesla is implementing a policy of non-cobalt utilization. I was wondering what kind of substitute do they intend to use instead of cobalt?
Yes, thank you very much. This is a very good question. And actually, they're trying to implement like solid batteries that, of course, are not using cobalt. But the problem is this one, because they're trying to understand which other metals could substitute cobalt, and especially its chemical qualities that are really unique. So they're trying to test some materials, but as I was saying before, this requires really long testing times, because due to the unique properties of cobalt, just to test these new metals, just to rope them up, it's not so feasible in the short time. So they are trying, of course, also to make this solution in order to face the sustainability problems affecting lithium-ion battery supply chain. But the problem is like this one. Actually, it's really difficult to find a good substitute for cobalt, and the testing and research will require a lot of time.
You mentioned the sodium-ion batteries, but they come also from cobalt, right?
From cobalt, exactly. Yeah. They're trying to search for other solutions, but it's not so easy. So yeah, they're trying to say, okay, we are going to make zero cobalt battery in, I don't know, 2-3 years. But practically speaking, I think that in the short time, it's not so feasible. It's more a strategy to protect themselves from sustainability issues affecting the supply chain of batteries.
Thank you.
I have also a question myself, actually two. One is the following. The problems you have presented so well, about cobalt, how specific are of this industry, or how common are for other supply chains that refer to feedstocks or primary energy sources, or even non-energy sources like commodities, for instance, in the food industry, that suffer again from problems of concentrated production, exploitation of African or Southern world countries, informal sectors, corruption, etc., etc. Think about coffee or diamonds industry or commodities. So how specific are the issues that you have presented as for cobalt and not for other commodities that come from the South world?
Yes, thank you very much for your question. Yes, of course, this is a problem affecting a lot of materials, not only cobalt, but also other related metals such as lithium and copper, that is related to cobalt, but also other materials outside this category of metals. And I think that cobalt has a characteristics regarding the informal mining sector, because how can I say, in this sector in particular regarding cobalt, we have industrial companies, as we may find the extraction of other materials. But here I would like to put the attention on this case because there is a sector that is the artisanal mining sector that is completely unregulated. So these persons work in an abusive way on territories that often are a concession of the industrial sector. And it's a completely intricate case that in some ways a lot of attention should be focused, because it has also a huge potential also for the especially for the local economy. So I think that, yeah, sustainability concerns affects as I said, not only cobalt, but a lot of materials, metals, also in the food supply chain, as you correctly mentioned, and so on and so forth. But other than sustainability concerns, we have a crucial sector that needs to be regulated. Companies need to understand that they do not have to eliminate. It's not a threat, but it's an opportunity. And I think that, yeah, cobalt is like very complex and interesting also for this.
Okay, and the second very quick question, because then we're running out of time, is how available and how reliable is data about production from the Democratic Republic of Congo?
Yeah, thank you. Also, this one is a big issue since artisanal mining sector is difficult to trace. Regarding data, for example, about the production and reserves, is the reliable source that is the USGS Mineral Commodities Summary 2020. That is a reliable source. However, if we want to trace exactly, as I showed here, the output of artisanal sector, of course, yeah, we have some data, but for example, in the literature, a lot of scholars conducted on-field surveys in order to understand the magnitude of this sector. And of course, even more difficult is to trace the revenues and the real trade of large companies. And in this research, in order to analyze the sustainability concerns, this one, I used the allegations reported in the Transitional Mineral Tracker database based on allegation of large companies. But since the sectors are intertwined, as I showed you before, these issues are concerns also the artisanal mining sector. But yeah, it's a big issue. Tracing the real data is really a big issue due to the informal nature of this sector.
Thank you very much. So before the session will be closed automatically and we will be kicked out, I would like to thank all of you. We managed to stay on time. We have 1 minute left, actually, or less than 1 minute. Thanks all of you for the presentation. Unfortunately, there were not many attendees, external attendees, but we have all enjoyed the presentation of the presenters. And thanks again, and thanks IEA for organizing this conference in this strange period. Let's hope the next year it will be much better for all of us. Goodbye.
Thank you very much.
Bye. Thank you.
Thank you. Bye.
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 Bye.